Module 3.2, Wavelength and the Wave Equation. When we did the lab last Friday, you looked at waveforms on the oscilloscope. This was the result of air moving back and forth. You were watching the result of a change in air pressure varying over time. Imagine now that I am shaking a jump rope. We'll use this as a model to help understand what happens when a guitar or a piano string is plucked. If I move the jump rope up and down in a regular fashion, using simple harmonic motion, I get a sine wave that travels the length of the rope. Now, let's take a picture and freeze that rope in time. Since this represents one moment in time, if we measure the length of the sine wave, we are now looking at length, not time. And so we call this measurement wavelength. We use the Greek letter lambda to represent wavelength. Wavelength is length, so it is measured in meters. The wave takes a certain amount of time to travel down the rope. The time it takes to travel one complete wavelength is the period, t. Many moons ago, we spoke about velocity and defined it as distance over time. Since a wave takes one period to travel one wavelength, we can replace d with lambda to get velocity equals wavelength over time, and we can replace time with the period, which gives us velocity equals wavelength over period. If we know the wavelength and the velocity, we can find the period by manipulating the equation, and we get period equals wavelength over velocity. Now, this is acoustics, so we are usually interested in finding out the frequency. Since period is 1 over the frequency, we can flip the equation to get the most important formula of this course, what I'll call the wave formula, which is frequency equals velocity over wavelength. Make sure you know this formula well. We will use it all through the course. So what does this formula mean? The big picture. Frequency is directly proportional to velocity. So as velocity increases, frequency increases. Frequency is inversely proportional to wavelength. So as wavelength increases, frequency decreases. Let's get a little feel for wavelength. With a little algebraic manipulation, we get wavelength equals velocity over frequency. We said the speed of sound in air is 343 meters per second. The lowest note of a piano has a frequency of 27.5 hertz. So the wavelength would be 343 meters per second divided by 27.5 hertz, which equals 12.5 meters. So what does that mean? A meter is a little more than 3 feet, so 12.5 meters is about 41 feet. That's about the same length as a standard telephone pole. On the other hand, the highest note of a piano has a frequency of 4,186 hertz. 343 meters per second divided by 4,186 hertz equals 0.08 meters. That's the same as 8 centimeters, or about 3 inches long. So you can see the range of wavelengths of sounds that we can hear is pretty large. To review, wavelength is the length of one cycle of a wave. Frequency equals velocity over wavelength. Frequency is directly proportional to velocity. Frequency is inversely proportional to wavelength.